Bismillah ar-Rahman ar-Rahim. A is a parameter between 0 and 1. We are interested in the integral x from 0 to infinity, the hyperbolic sine of x divided by x times the hyperbolic cosine of x over a. Let's start by writing this ratio explicitly in terms of exponentials. The hyperbolic sine of x is e to the x minus e to the minus x over 2. The hyperbolic cosine of x over a is e to the x over a plus e to the minus x over a divided by 2. Multiply the numerator and denominator by e to the minus x over a. Downstairs, we get 1 plus e to the minus 2x over a. Upstairs, we get the difference between these two exponentials. If alpha is between 0 and 1, we can expand 1 over 1 plus alpha as summation j from 0 to infinity minus 1 to the j, alpha to the j. X and a are positive, so this is a positive real number less than 1. We can use this expansion. We have these two exponentials times summation j from 0 to infinity minus 1 to the j, e to the minus 2xj over a. Multiplying by this bracket, we get summation j from 0 to infinity minus 1 to the j, then the difference between these two exponentials. The integrand is this ratio, given now by this sum, divided by x. Let's assume that we can integrate term by term. Thus, omega is summation j from 0 to infinity minus 1 to the power j, the integral from 0 to infinity, 1 over x, multiplied by the difference between these two exponentials. Consider the integral from 0 to infinity of e to the minus alpha x minus e to the minus beta x divided by x. We can write down the integrand as integral from alpha to beta of e to the minus xu du. Assuming that we can interchange the order of integration, we get integral from alpha to beta, integral from 0 to infinity, e to the minus xu dx du. The inner integral now is 1 over u. When we carry out the integration and use the limits of integration, we get the natural logarithm of beta minus the natural logarithm of alpha. This can be written as the natural logarithm of beta over alpha. Going back to our problem, we have integration x from 0 to infinity, 1 over x times the difference between the exponentials. So the result is the logarithm of this quantity here divided by that one. Log 2j plus 1 over a plus 1 over 2j plus 1 over a minus 1. We can multiply the numerator and denominator by a to obtain that omega is sum j from 0 to infinity minus 1 to the j log 2j plus 1 plus a divided by 2j plus 1 minus a. To get rid of this minus 1 to the power j, we can write down the summation j from 0 to infinity. We can replace j by 2j to account for the non-negative even integers. In this case, minus 1 to the j is equal to 1. So we have plus 1 times log 2 times 2j. That's 4j plus 1 plus a divided by 4j plus 1 minus a. Then to account for the non-negative odd integers, for those minus 1 to the j is minus 1. So we have plus minus 1. Now we replace j by 2j plus 1. 2j plus 1 plus 1 plus a, 2j plus 1 plus 1 minus a. We can combine the two logarithms. We have 4j plus 1 plus a over 4j plus 1 minus a. Then we have this guy here. That's 4j plus 2 plus 1 minus a, which is 4j plus 3 minus a. Finally, we have this term, which is 4j plus 3 plus a. If we replace j by j minus 1, our sum goes from 1 to infinity, and every j is replaced by j minus 1. Omega is equal to summation j from 1 to infinity, the logarithm of 4j minus 3 plus a times 4j minus 1 minus a. Downstairs, we have the product of 4j minus 3 minus a and 4j minus 1 plus a. This result is related to the cotangent function. The key to establish this relation is the product formulas for sine of x and cosine of x. The natural logarithm of cotangent by 1 minus a over 4 is the logarithm of cosine by 1 minus a over 4 divided by sine by 1 minus a over 4. If x is equal to pi 1 minus a over 4, we get by 1 minus a over 4, the product j from 1 to infinity, 1 minus pi squared. It goes away with this pi squared. We are left with 1 minus a all squared divided by 16j squared. Because we have the sine function downstairs, then this term, after taking the logarithm, is here, minus log pi 1 minus a over 4. When the logarithm is applied to the product, we get the sum of logarithms. This term is this one here. We do the same for cosine by 1 minus a over 4. We go here and replace x by this quantity. We get this numerator. Inside the logarithm, multiply upstairs and downstairs by 4 times 2j squared. This 4 times 2j squared in the denominator can be multiplied by this quantity to give us the difference between these two squares. We also multiply by 4 times 2j minus 1 squared over 4 over 2j minus 1 squared. We use this so that the numerator now is written as 4 times 2j minus 1 squared minus 1 minus a squared. Outside, we have this ratio here, which is 2j squared divided by 2j minus 1 squared. We have a difference between two squares in the numerator and in the denominator. The brackets that we get are 4j minus 3 plus a, which is like this one in the expression of the integral omega. 4j minus 1 minus a, here it is. 4j minus 1 plus a, here it is. And then this one, which is 4j plus 1 minus a. In the expression for big omega, we have 4j minus 3 minus a. What we do here is to multiply by 4j minus 3 minus a over 4j minus 3 minus a. This 4j minus 3 minus a in the denominator, together with those guys, those are the argument of the logarithm indexed by j, and this summation here is exactly the integral of interest omega. Now we have this minus log by 1 minus a over 4, which came from this x in the product representation of the sine function. Then we have a sum j from 1 to infinity log 2j squared over 2j minus 1 squared. We also have 4j minus 3 minus a in the numerator and 4j plus 1 minus a in the denominator. There is a known result that the following product is convergent. The product j from 1 to infinity 2j squared over 2j minus 1 times 2j plus 1. Specifically, this product is equal to pi over 2. Inspired by this, what we can do is to multiply and divide by 2j plus 1. From this 2j minus 1 squared, we take 2j minus 1 together with this 2j plus 1. Now we have something that looks exactly like this. We also get 2j plus 1 divided by 2j minus 1. We can write the logarithm of the product of these two quantities as a sum of logarithms. Then we write each series as a log of a product. This product is pi over 2. For the second product, suppose that the product stops at big J, and then we take the limit as big J tends to infinity. When J is equal to 1, this ratio is 3 to 1. When J is 2, this is 5 to 3. When J is 3, this is 7 to 5, and so forth. When small j is equal to big J, then we get 2 big J plus 1 over 2 big J minus 1. We have cancellations. The surviving term is 2 big J plus 1. We also have this ratio here. This is 1 minus a over 5 minus a times 5 minus a over 9 minus a times 9 minus a over 13 minus a. We also have cancellations. The last ratio is 4 big J minus 3 minus a, which goes away with this term here. And downstairs, we get 4 big J plus 1 minus a. The surviving terms are this 1 minus a and this 4 big J plus 1 minus a. If we take the limit, we have 1 minus a, limit j tends to infinity, 2j plus 1 over 4j plus 1 minus a. The limit is 2 over 4, which is 1/2. The argument of this logarithm is 1 minus a divided by 2. If we combine this with that, we get log pi over 2 times 1 minus a over 2. That's pi over 4, 1 minus a. These two terms cancel. So omega is exactly the natural logarithm of the cotangent of pi 1 minus a over 4.